The producers and distributors of Tech AV technical training aids welcome you to this, the first program in the Basic Refrigeration series. This is the overview program in which you will be shown how a typical commercial refrigeration unit operates. You will gain a working knowledge of a modern evaporative refrigeration system. In our attempt to introduce you as quickly as possible to the real world of refrigeration, we shall begin this overview by looking at a typical commercial plant, set up purely for demonstration purposes. What we're looking at is technically termed an air-cooled, semi-hermetic vapor compression commercial refrigeration unit. At the end of this module, you will be able to identify each component in a system, explaining the purpose and the working principles. This knowledge will help you when you become involved in maintenance, repair, or installation procedures. To understand the working principles of refrigeration and air conditioning systems, you must at least understand certain scientific facts regarding heat and heat transfer, especially in regard to liquids and gas or vapor. Heat is an energy form that exists in every substance here on Earth. Heat is always on the move. As long as a temperature differential exists between substances in proximity, the heat will move or transfer out of the warmer and into the cooler substance. To help illustrate this, take a block of ice into your hand. It feels cold. But why? Well, the temperature of the ice is 0 degrees, but the temperature of your skin is around 38 degrees. A large temperature differential exists, and because of this, the heat in your skin transfers into the ice. Another example is to hold a mug containing a hot liquid. The temperature of the mug may be around 70 degrees, that is 30 degrees more than your skin. It is your skin that now has the lower temperature. Therefore, heat will flow into your body, resulting in the hot sensation. A very simple refrigeration unit is the cooler box. If a block of ice were to be placed inside the box, then any heat contained in the air will move into the ice and the air will cool. Any warmer object placed into the box will release its heat to the air. A cycle of heat transfer is set up that will continue until all the substances in the box reach a common temperature. All of the heat originally introduced is still inside the container. As we'll see shortly, a true refrigerator removes the heat and discards it into the atmosphere. Another very basic concept that we need to understand concerns liquids, specifically when subjected to heat and pressure. The commonest liquid that we all know is water. We also know that water can easily be heated using any heat source, such as a gas flame. Obviously, the gas flame has a far higher temperature than the water, which means that heat is going to transfer into the water. As heat moves from the flame into the water, there will be an increase or a rise in the temperature. The heat used to do this we call sensible heat, so named because it results in a change of temperature that can be measured. The temperature will continue rising until the water reaches what is technically known as saturation point, or in common terms, it reaches boiling point. At sea level, water boils at around 100 degrees Celsius. Up until the time that the full mass of water has been raised to 100 degrees, all the heat applied to the liquid is sensible heat. Any further heat added to the liquid after saturation point has been reached is called latent heat. Latent heat does not increase the temperature. Instead, it will maintain a change of state in the water. Change of state means, in our case, that the liquid is changing into its vapor form, also called vaporizing. The opposite of vaporizing is known as condensing. Condensing is the term used to describe vapor as it changes state back to the liquid form. This occurs when the latent heat in the vapor is lost or given off. If we could return the entire mass of vapor back into liquid, then the amount of latent heat given off during condensation would equal the latent heat absorbed during vaporization. Let us briefly summarize the main points so far discussed. Heat always moves from a higher temperature to a lower temperature. The heat required to change temperature is known as sensible heat. The heat involved to maintain a change of state is called latent heat. During the time that a liquid is changing state into a gas or vapor, it absorbs latent heat. The liquid is said to be evaporating. When reverting to a liquid, vapor is said to be condensing. During the condensing phase, any latent heat contained in the vapor is removed or given off. Let us now consider how pressure affects the saturation points of liquids. All around us is a pressure called atmospheric pressure. Atmospheric pressure is the force exerted upon everything on the surface of the earth, caused by the sheer mass of the air which surrounds our planet. At sea level, this force is a little more than 1 kilogram per square centimeter. In practice, we use the term kilopascals. For calculation purposes, atmospheric pressure is considered as being 100 kilopascals. This demonstration is being conducted close to sea level. The water is boiling, and the temperature reading is a fraction over 100 degrees. In the next demonstration, we shall see how a drop in pressure affects the saturation point. With the aid of a vacuum flask and a vacuum pump, we will be able to reduce the pressure acting upon some fresh water to a partial vacuum. The pump is busy extracting air out of the flask, and that is basically how pressure is reduced. The formation of bubbles indicates that the water is reaching its saturation point. The temperature of the water remains at ambient or room temperature, proven here by the fact that we can handle the flask without discomfort. From our demonstrations, we can deduce that by changing the pressure acting on any liquid, we effectively alter the liquid's saturation point, or, if you prefer, the boiling temperature. A very definite mathematical relationship exists between pressure and the saturation point of water that can be plotted graphically. Every type of liquid, both natural and synthetic, will have its own unique saturation temperature at any given pressure. Utilizing these scientific facts, we can create the conditions for true refrigeration. Liquids used in evaporative refrigeration systems have very low saturation points. A typical refrigerant, used commonly in many commercial systems, is a type called refrigerant 22, or simply R22. This refrigerant, at atmospheric pressure, will boil vigorously at a temperature around -40 degrees. The principle of a mechanical refrigeration system is largely a matter of manipulating or controlling the pressure acting upon a refrigerant moving within a closed system. The process causes refrigerant to evaporate in one area, and therefore absorb heat, and to condense in another area, where it gives off heat. Refrigeration, in basic terms, is the process of removing heat. What an air conditioner does is to remove the heat from the air as it passes over cooling coils, and then return the cooled air back into the room. The operating principles resulting in cooling are virtually identical in both air conditioners and refrigeration units. After the break, we will discuss the principles of the mechanical refrigeration cycle.